is it necessary that all this quantumness is harmless for subsequent evolution? Meaning, what happened to those correlations? And can I ignore those correlations completely in order to say that evolutions later on of the universe will remain classically prescribed? Okay. Once this problem statement is clear, the remedy towards addressing this is one of the famous approaches of stochastic gravity, where you envisage that there is some stochastic term which is present on your right-hand side of Einstein's equation. Typically in semi-classical gravity, what we do, we take the expectation value of T mu nu on the right-hand side, and we forget about the fluctuations in T mu nu. Okay? This would give me a remedy towards working with a defined expectation value of T mu nu or classical-like stress energy tensor. But in principle, there is a possibility of a fluctuating term over there, which is rather well described in this living review paper by Hu and Verdager, where you add a stochastically fluctuating term, this xi AB, and ask for a consistency solutions of this Einstein's-like equation after invoking first-order fluctuation. So you account for a tiny fluctuation. You do not let it overpower the expectation term, but still you want to see invoking this kind of expectations and fluctuations, how much of distortion I can generate in classical evolution. Okay. So one good route of assessing whether this can be ignored or this should be retained goes by analysis of something called a noise kernel. Noise kernel effectively is the two-point correlation of this fluctuation term, and the strength of noise kernel is measured against the expectation value of TAB to decide whether you want to keep it on the right-hand side or not. Okay? So ultimately, we want to see the deviations of the TAB, the true TAB, from its expectation value. So the TAB expectation value is typically fed into the right-hand side. Truly, quantum mechanically speaking, the full TAB operator should be there with all its correlators and all its fluctuations. So we want to know how different these two things are and how different their correlators would be, and this thing is captured by the noise kernel. So the idea would be to compute the noise kernel and try to see whether it competes well enough with the expectation value or not. If it is many orders down, then probably there is no case to worry. But suppose it starts becoming strong enough, then you have to revisit your question and assessment of using Einstein's field equations or Friedmann equations as a viable tool of taking things forward. Okay, so now this is in a work we could show that the noise kernel which we are after to assess the stochasticity of the system can be obtained from the two-point functions gxx prime and gyy prime at two different points. You compute the quantum correlators and then run it through some derivative machinery. You can see that this operator acts on the two-point function, and then you have to take the coincident limit in a sufficient alert way so that you do not generate some artificial divergences which are very common in quantum field theory. But if you do it consistently and correctly, you will get the strength of the two-point correlator of the fluctuation, which is the noise kernel. So ultimately, the two-point function of the field would have a say how much of noise kernel it would generate and how much of the noise kernel is generated after these derivative operators hit it twice. Okay? So this is what we can do, and we can go after different fields in cosmological settings and try to see what happens when the noise kernel is computed out of it. Okay, so let me just backtrack a bit and let us go for the inflationary era for the brief thing to see whether inflationary analysis, what we do typically, is safe against that back reaction or not, whether the noise kernel in the inflationary domain is under control or not. So I would go and compute the two-point function of the field in the de Sitter-like environment, because inflationary era is supposed to be borne out by a de Sitter-like expansion. So if I do that, remember this G is supposed to be known, which will be hit upon by this operator. So I compute this thing. So I'm just giving you a result which you can just straight away compute for a massless, let us say, a scalar field in de Sitter spacetime. And this has been a very long debate about the character of the two-point functions of massless fields in de Sitter background, which has a very peculiar structure. So typically, if you do in the flat spacetime, the two-point function of a massless scalar field is proportional to inverse of the geodesic distance squared. Okay, which I'm calling y. So there is a 1 upon y kind of suppression in the two-point function de Sitter, which is common to flat space-time as well. However, there is this secular term 2 over delta, where delta is your proximity towards the de Sitter era, how close you are about the de Sitter era. If delta is 0, you are perfectly in the de Sitter universe. If delta is slightly away from the 0, you are slightly away from the de Sitter, quasi de Sitter. So depending upon how close you are in the inflationary domain, how close you are to the de Sitter era, that will generate this amount of quantum correlations. And you can see closer you are to the de Sitter era, larger is the correlator due to this secular term. And this has been a topic of a huge debate, whether these states have a meaningful role to play, or how do we assess this state's infrared divergences, because at large distances as well, where all other terms die off, this survives. So therefore, you have a leftover quantum correlations even at infinite distances. That is a particular property of de Sitter spacetime. And this is not a rewardless property. We know that this property, if you write it in the Fourier basis, it comes from a particular term in the Fourier domain, which just signifies that you have an infrared divergence in the two-point function. So this infrared divergence popularly goes by the name of scale invariant power spectrum, what inflation should generate. So the scale invariance power spectrum, what we see in the CMB data more or less, is a testimony to the fact that the universe was born in a state not much different quantum correlator than this. Our analysis that the tilt to the power spectrum is directly related to this delta. And that tilt is very small and close to 0. That looks like the universe was indeed born in a de Sitter-like phase. And it indeed has a long-range correlations. So therefore, it should worry us if the two-point function has a divergent piece in it. It looks like that it is capable to generate large amount of noise kernel, because two-point functions acted upon by the derivative operators would generate how much of noise kernel would be. However, we can be a bit relaxed, because if we just go back to this thing for massless field, this term will drop out, and therefore I will be just left with this derivative terms. And this two-point function, which is given for massless fields, the derivative term will just kill this divergence, because the delta, I would use it to shrink towards 0 after taking the derivatives, or you can fix your space-time to be quasi-de Sitter. So on those space-times, despite the two-point function having a divergent structure, there will be no divergent noise kernel, because derivatives will kill it. So it is called secular divergent term and harmless divergent term. Okay, so far so good. So inflation story is intact. There is no hard back reaction against the inflations analysis. So it is not supposed to go haywire. You can use semi-classical analysis. Now the question is, what do we do if we are not in de Sitter kind of era, subsequent evolution, let us say radiation dominated era, matter dominated era, or dark energy dominated era? So there again, the same thing we should do. We should try to find out a matter field or some field, which is, let us say, a scalar field, massless, and we want to know the two-point functions character in those space-times. So there, in way back some 6 years back, along with Paddy, we came up with a nice duality which we could propose, that there is a strong correlation between massless fields in FRW universes to massful fields in de Sitter universes. So this duality works like that if you give me an action of a massless scalar field in any power law FRW universe, whose scale factor goes with some power of conformal time or even with co-moving time, that scalar field's description through a conformal transformation can be cast upon into a form where you are living, the scalar field has changed by a conformal factor this much and has become psi of x, and that psi of x lives in a space-time depicted by a tilde, the scale factor being -1 over h tilde, which is a de Sitter kind of universe. So just starting from a FRW universe, do a conformal transformation of this kind, you will land up on a description which is equivalent to a massive field in de Sitter spacetime. So therefore, if I am interested in knowing about the quantum field's correlators in FRW universe, I should rather look for massful field in de Sitter and their correlators. And using the conformal map, I can regenerate the correlator structure in any FRW era, matter dominated, radiation dominated, and whatnot. Okay, so this is what you land up with, that in power law FRW universe, whose scale factor is given by that, the two-point functions of a massless scalar field is related to a massive scalar fields in de Sitter space-time massive scalar field 2-point function up to this conformal factor, where mass of the scalar field in the de Sitter domain is obtainable from the power index of your FRW universe. So the mass of what FRW universe you started with is equivalent to knowing how much of mass it will be equivalent to in the de Sitter case. Okay, and this has a rather interesting kind of a structure, that effective mass, the effective description in de Sitter is controlled by a mass parameter which is related to this power law. Now you can see various interesting cases from here. For example, suppose I want to look at the de Sitter universe itself, that my starting universe is also de Sitter. A massless field in de Sitter is equal to Q is equal to 1. For that case, the generated mass is also 0, because you start from a de Sitter massless, you will land up in de Sitter massless. So it's a trivial duality. But if you are interested in, let us say, radiation dominated era, that in these notations is equal to Q is equal to -1. Q is equal to -1 would be effectively dual to a massive scalar field of mass root twice of the h, the Hubble parameter of the de Sitter. And this is a very interesting mass, because root 2h in the de Sitter era is known by the conformal mass. At this mass scale, things become flat-like. So therefore, in radiation dominated era, massless scalar fields are supposed to behave conformally dual to a flat field space theory. So they would not have interesting things which we are talking about. They will behave as if they are doing things business in flat space time. So pathologies or the divergence of flat space will be controlling the divergence of 2-point functions, and we know in flat space the divergences in 2-point functions only appear at the UV end, not at the IR end. So at the infrared sectors, large wavelength sector where CMB data is being monitored, nothing interesting to happen in the radiation dominated era. In the matter dominated era, Q is supposed to be -2. This is another interesting limit, that you put Q is equal to -2, you will find that again you will get effective mass is equal to 0. And this is very strong coincidence, that the massless field in matter dominated era is dual to again a massless field in a de Sitter era. And we just saw a couple of slides back that the massless field in de Sitter era came up with a divergence piece which was harmless. However, in matter dominated era, not only the 2-point function of the massless scalar field will come, there will be coming a conformal factors which will make the divergence more serious this time. The divergence terms in the correlator comes up with space-time dependent conformal factors, and therefore this time they are not going to get washed out under derivative actions. Remember, in de Sitter we argued the secular divergence term was devoid of any space-time dependency, so therefore when the derivative operators hits them, it will be killed. Not this time. Matter dominated era would have these conformal factors which will undergo the derivative action and they will survive. So therefore, one has to be careful while throwing them away or looking at them. So what we did, we classified for all the cases what is the character of the noise kernel. From this 2-point function, I will do this double derivative operations and quantify how much of noise kernel I am expected to generate out of it. So here is the list of, in different space-time, what we can expect as the universe grows. Okay, so I'm just classifying in a couple of subsets. The scale factor in the power law cosmology is given by this -q. For any q which is between 0 and 1, you would see that the late time here means eta tending to 0. Scale factor will become very large for q between 0 and 1 for eta tending to 0. So late time means here in this subset eta tending to 0. So you compute the 2-point correlator of the fluctuations of stress energy, which is the noise kernel, and you will find out this structure over there. You can see that there is a outside eta to the power 4q minus 4 and inside the opposite of that 4 minus 4q. So they exactly cancel. And when you take eta tending to 0, this first term survives as a constant. Nothing happens to the first term because there is no eta dependency in the first term. That will survive. Just like in de Sitter, remember, there was a term which was surviving, which was not being killed out completely. So between 0 and 1, you will have a remnant noise kernel. They will not be completely wiped out at late times, but you will be surviving with some non-zero value. For q is equal to 0, which is flat space-time, scale factor becomes 1 and not changing in time, you will get this noise kernel structure, which is very standard. You will get the 1 over distance to the power 8 kind of thing. There is no spatial dependency locally, meaning it is just separation dependent and no temporal dependency. You increase your distance, your correlators will go down, which is almost fine with the flat space time. The interesting bits start when you cross over to the other side, when Q is in the negative domain. Between -2 to 0, you will see that now this time the scale factor, since it has come up with a positive power overall, because your Q has turned negative, your late time era is eta tending to infinity, not eta tending to 0. So therefore, we have to look for these pieces rather carefully. You will see that all these terms are coming with certain powers which will become divergent at late times. Okay? So for the power laws between 0 to -2, these are not safe space times. They have large noise kernel or large quantum back reactions. One particular case, which was matter-dominated era, Q is exactly equal to -2, and there, even before going to late time, there are terms like depending upon 1 upon epsilon. Epsilon is here 2 plus epsilon. Q is -2 plus epsilon. So you get closer and closer to matter-dominated era. There is a term in the noise kernel which will start diverging even at finite time, not only late times. So that tells you, if you are really living in a universe totally dominated by matter and your effective equation of state is crossing 0, it looks like momentarily noise kernels will rise up to something. They will just light up the solution space and they will try to put a kick to classical evolution. You will not be allowed to continue classical evolution throughout and cross -2 safely. -2 of Q, which is the matter dominated era, which is also equation of a state crossing 0 for the whole universe, is a place where classical equations of motions are supposed to get a jig. They are supposed to get a distortion around that time. Okay, so this is a cartwheel of which space times are safe under back reaction and which are not. For example, as we discussed, for any Q which is between -2 to 0, so you will see that these noise kernels are 0. These noise kernels are at late times are 0. At Q is equal to 0 is flat space time. Between Q is equal to 0 and 1, there is a reminiscent constant leftover noise kernel. However, there is a huge window of between -2. So effectively, you start with -2 up to Q is equal to 1, which is equivalent to equation of a state being 0 to 1, -1/3, and then -1/3 to -1. These universes dictated by these equations of state not only come with interesting things. For example, -1/3 to -1 we know is accelerating universes. So not only they cause acceleration, they will cause revival of the noise kernel or deviations from the classical evolution. So you should not take the classical evolution generated by expectation of Q mu blindly. Secondly, this is the story of a massless field. So whatever massless field you think of, they will generate the similar kind of divergences in the noise kernel, and they will have appreciable say in the dictation of the evolution of the universe. So we can calculate what would happen to vector fields, let us say U1 electromagnetic field, or a spinor field, or a tensor field. Since we know the vector field, for example, electromagnetic thing, in 4 dimensions, they are conformally flat, and FRW universe is also conformally flat. So they do not depict anything significant. So their correlators remain as if they are in the flat space-time up to conformal factors of scale factors. So there, nothing interesting happens. You can see from that argument, spinors are also safe from roughly the same argument, because spinors are square root in some sense of U1 field. Okay, so these two space-times, these two kind of fields do not generate appreciable back reaction. A scalar field does, and the next analog which will do it would be the components of a tensor field, gravitational waves. So gravitational waves treated quantum mechanically would suggest in the de-Sitter kind of phase, you would not have appreciable back reaction from them, quantum mechanically speaking. But in matter-dominated era and later on, which is the dark energy-dominated era, you cannot wish the stochastic corrections coming from the gravitational background away in the quantum evolution. So they are not going to land you into the classical equations of motion if you just account for them systematically. So this is just a story of how things will unfold if this will happen in this way, that massless scalar field or massless tensor fields are going to affect your evolution story. We also proposed what would be a witnessable signature of such a thing happening. So remember what we are saying, that as the universe progressed from radiation dominated era, by the way, had nothing to worry about because all the back reaction was under control. Interesting thing happens once you cross the matter dominated era, in the sense of equation of state crossing omega effective equal to 0. There is a brief moment where these correlators will grow, become large, and disrupt your classical evolution. So there is a possibility of a momentary disruption in the evolution story of the universe. And where should this show up? So in the morning talk, Daud had a very nice description of this Fermi coordinates and Fermi normal coordinates, Fermi derivatives as well. I'm just going to use that machinery. Actually, I am not the first person to use that machinery. Way back in 80s, Leonard Parker tried to understand what will happen to hydrogen atom if it is put into expanding universe thing. So there is a Coulomb interaction which is trying to hold things together, and there is a acceleration of the universe. Suppose you're talking about a universe, empty universe, when the structure has not formed. So you have just hydrogen atoms here and there. So he introduced via the machinery of Fermi normal coordinates. Again, I'm skipping it over for the time constraint, but if anyone is interested to learn more about it, I'm happy to talk. So it will give rise to this kind of extra term in the Hamiltonian evolution of an electron bound by the Coulomb potential of a proton, let us say. And this showed from this analysis, actually, this perturbation is way too weak to do anything meaningful to the hydrogen atom. So the hydrogen transition lines virtually remain unperturbed. That means given FRW universe, let us say, even in the radiation dominated era or last scattering surface where hydrogen was really being formed, the curvature was not too great, and these terms were not too appreciable to do anything meaningful to the hydrogen. So therefore, hydrogen atom, as we know in our lab, is exactly more or less the same hydrogen atom which was formed at last scattering surface. Okay, so this is one thing, that the transition lines or eigen spectrum does not get meddled too much. However, in addition to that, what we anticipated, what it should do is to cause transitions. Just like if you put an electric field in the background of a hydrogen atom, weak electric field is not supposed to give appreciable change in the eigenstate, but you will have a dipole transitions generated by that electric field. The same should be done by the gravitational perturbations as well. So you do the linear perturbation theory around the FRW background and try to find out the form of the perturbation Hamiltonian in terms of a gravitational wave if it passes by in an FRW universe. So you will see that this extra term can be written in terms of FRW parameters A dot and A double dot, and H dot and H double dot. This is the gravitational perturbation theories terms. Put together, there are some Hamiltonian times positions double operators. So if you are careful enough, you will see that this is roughly counting the quadrupole moment of hydrogen atom. Okay. So quadrupole moment, as you know, would couple to gravitational wave, just like dipole moment couples to the electric field. And you can do the computations, find out the selection rules for this kind of Hamiltonian, and try to find out what would be the transition probability corresponding to a gravitational wave passing by. Okay, so this is some computation. You compute the gravitational perturbations 2-point correlator this time, and it would have this structure as we discussed, the 2-point function hit upon by those derivative terms which we saw before. And ultimately, you will find out again that the transitions caused by graviton will depend on parameter delta inversely. That delta is your proximity to being in matter-dominated era. So if delta goes close to 0, you will see that transitions in hydrogen atom, for example, will be lighting up by the gravitational channel. So graviton channel will be the most efficient channel to do this transition. For example, you can do the same exercise for dipole transitions. So you can find out what is the dipole transition probability, and it is, since dipole transition talks to electric field in FRW is exactly similar to electric field in flat space-time. So therefore, you will not see anything interesting happening from the electric field side. That transition rate will almost remain the same as it is in the flat space-time. However, gravitational driven transitions, gravitational perturbation theory will say that during matter-dominated era, there is something interesting about to happen. So you can calculate individual rates. This is the graviton-driven transition rate, which talks to the quadrupole moment of hydrogen has fifth power of frequency dependency, and then some power factor depending upon which universe you are. Remember, Q was the scale factor parameter. A eta was h eta to the power minus Q. Similarly, you can do the electric field driven transitions in hydrogen atom, and you will get the famous frequency cube relation and this space-time curvature dependent terms. And now you can ask which one is dominant. So I compute electric field driven transition divided by graviton driven transitions. You do this computation in flat space, you will get the famous relation by Scully that you will get 10 to the power 39 orders, which is the hierarchy problem, that graviton transitions are 10 to the power 39 or 40 orders suppressed compared to electric transitions. So far so good in flat space-time. If you do the same analysis in FRW universe, you will get this relation. And again, you can see if you go really close to matter-dominated sector, era which is very close to matter-dominated sector, let us say delta close to minus 10 to the power minus 6. That means Q is minus 2 plus 10 to the power minus 6. There you will find out the flip happens. This is one place in the universe, in the entire timeline of the universe, where graviton-driven transitions overpower electric field-driven transitions, and it will momentarily heat up the available hydrogens at the redshift of roughly between somewhere 20 to 40. So this is, I have plotted effective equation of state of a universe by assuming, let us say, whatever evolutionary story of a universe is being dictated by a scalar field, dictated by a perfect fluid with equation of state parameter omega. You will see across various different models, most of them will cross effective equation of state omega close to, cross omega is equal to 0, somewhere between redshift of 20 to 40, depending upon your model of cosmology. So amongst those models of cosmology, there is a place somewhere where graviton-driven transitions were super powerful against anything else. Other fields behaved as they behave in flat space-time, more or less, regularly. Graviton-driven transitions did not. So there is one opportunity, as we try to put out, where you could look interesting phenomena, heating up of hydrogen. So for example, the last talk we were hearing about 21 centimeter emissions. Maybe this kind of heating has disrupted the thermal balance they had set up with CMB background, and some other hotter kind of species or graviton took over the transition redistribution there happened, and it may or may not lead to a surplus of radiation from this era, 20 to 40. Okay, so just to wrap up things, apart from this semi-classical back reaction, one can compute various other things as well. We had done some analysis of full-blown quantum gravity computations as well, and you want to know whether quantum gravity is under control or not. And there are many signatures which suggest not only quantum back reactions of quantum matter starts becoming important in the late time era of cosmology. There are preliminary hints, some of the works we have done and some other groups as well, which are suggesting even if you do canonical quantum gravity analysis, they also suggest that the late time universe, particularly universe crossing the omega is equal to 0 in the effective equation of a state, may not be tolerant towards classical analysis. So they might have hidden, which are or growing up quantum back reaction, quantum correction, which may become important. Okay, so I wrap up with this take-home message that first of all, as we discussed, even the appearance of a classical thing from a quantum seed is perplexing. There is no clear idea why the universe became classical. There is only mathematical techniques where we can argue that expectations levels can be generated out of classical ensemble averages. However, once you accept this idea that somehow some mechanism made the universe classical after the end of inflation, it looks like the later on eras are not as innocent as we used to think. Radiation dominated era is slightly sympathetic towards maintaining that equilibrium. It does not grow or decay anything. However, matter dominated era and onwards, quantum revival seems to be possible in all sectors, matter, including matter, semi-classical matter, or quantum gravity. So therefore, the take-home message or punchline of this talk will be that late time epoch may not be as innocent as we used to believe for semi-classical back reaction or full-blown quantum gravity computation. Thank you. I'll be happy to take any questions if you have.
So any question?
There is.
Does all the calculation means that you accept the conception of statistical classicality
Because if, for example, there is some full classicality due to some kind of collapse of wave function or something like that, then nothing should happen in classical area. Is it true?
So there are two things. So this is a very good question. So there are two things. So first of all, when we do expectation value analysis, there are two different questions: what happens during the measurement process and what is the outcome. So there are various proposals which suggest a dynamical model of a quantum collapse using non-unitary quantum mechanics or any other process. So they do suggest if something interacts with a macroscopic object, the measurement process, that collapses the wave function. However, in the expanding universe, we do not have an understanding whether we should be applying the collapse of the wave function sans any measurement. So all the measurements what we are talking about are supposed to happen in very late time era of cosmology when we started looking at it. So there is no a priori reason to believe why there should have been a wave function collapse at an early phase of the universe. And even if there was some mechanism, something called a continuous spontaneous localization of the wave function, that will just suggest that it will momentarily bring you to the collapsed kind of eigenstate description of some viable operator. It is not very clear because of the lack of their covariant techniques that whether once a system is driven into a collapsed kind of description, it will remain there for eternity. The non-trivial evolution of the universe may or may not, I do not know the answer to, can revive it once again as well.
Okay, I just had a small comment or a question. So when you did the duality or the correlator calculator, every time you took the phi square potential, like the square potential, I believe?
No, so actually, so the duality stands irrespective of the potential. So the statement is right now about, okay, the statement is about right now the action I had written was for a free field theory for demonstration.
Yes.
The duality will take you from one, so if you add interactions or potentials, you will take, the duality will take you from one potential configuration to another potential configuration, that's all. For trivial massive kind of interaction, let us say phi square or phi to the power n, that potential remains the same, only its coupling constants change. So the duality works across various class of potentials and only the parameters.
So here itself, if I take a v phi, could you give me what is the duality of the d theta?
That depends upon what kind of v phi. So if you give me a power law phi n, then it will go to phi n again, but lambda which is coming in front will change depending upon that. So lambda phi 4, for example, is unperturbed. Lambda phi 4 will go to lambda phi 4 only.
And where the correlation you calculated also in phi square, is it can be generalized for phi n? I mean, I know that those are not UV complete, etc.
So if you are willing to do perturbation theory, you know the Wick theorem will tell you all higher correlators will be generated from the 2-point correlators put together and do the connection properly. So yes, so in free field theory or even perturbative field theory, all this structure will remain true.
Because you got the scale invariant power spectrum k squared because of phi squared. So that's what I am worried. If I take phi to the power 4 or something.
So that is the game of non-Gaussianity people try to look at, looking at higher correlators and try to test this idea whether higher correlators can be entirely obtained from lower correlators or not. In Gaussian theory or quadratic theory, they are supposed to be. But in non-Gaussian theory, higher correlators will be significantly different compared to the lower correlators construct. So that is somewhat observations will decide which way we turn.
Yeah, so see, with regard to the primordial perturbations, now Jerome Martin had a very detailed paper and their group. So to decide whether the perturbations were really quantum or they are just classically stochastic fields. So finally they found out that observationally, in principle, if you start from a classical stochastic field or you start from a quantum thing, the observationally the difference is of the order of 10 to the power minus 51 or 52. So in principle, you will never be able to decide whether this is quantum or classical. So, and you are talking about the quantum effects.
So, yeah, so two things. So two things to that. So yes, so there are some papers, so the Jerome Martin's group, so which I had also cited. So the claim is that there are some observables. So Jerome Martin and Vincent Finin paper, this one and even this one over here. So they argue that there are many of the entanglement operators which do not show you anything. However, they claim even in this set of data, there is a selected set of observables which do show up even today. This is not as small as 10 to the power minus 51. So they say that if you look at certain particular set of correlators in certain different observables, not directly on the temperature anisotropy, there some hiding signatures is there. Okay, and this is known for entanglement theory, that for entanglement to exist, not all entanglement pair of observables should show up. Any one of them is sufficient. So this group is also suggesting that you could in principle find out set of observables which give you stronger correlators or entanglement structure. So therefore they are saying that right now the idea is it is indecisive. The claim I am saying that even if these correlators are small, this is virtually a large scattering surface data. What happened afterwards, I am saying even you took anything which was non-zero but small, while crossing omega is equal to 0, which should happen around a restrict of 30 or so, they will, any non-zero number will be lifted up to various orders. So unless you know for sure there is nothing hiding in correlators, you have a thing to worry for what happens when the universe crosses omega is equal to 0.
So on what it would have impact? Let us suppose you some effects are, so in what way suppose?
So for example, I would say the growth of perturbations which we take to calculate, let us say, ISW effect or Sackville's effect in temperature anisotropy, that will be not governed by just perturbation theory around the classical analysis. You have to add a stochastic term over there to redo this analysis. So ISW effect or Sackville's effect, SW effects, what we understand is based primarily on the classical theory, and most of the interesting things start happening around redshift of 50 to now, where structures start appearing. Those analysis one need to have a relook at.
But quantitatively, how can we say that, let's see, how much would be the difference and so on and so forth?
So that is what,
Observationally.
yes. So observationally, I can give a prediction. So one prediction I have already outlined in the looking up, in this analysis suggests that hydrogens should be more heated than they are. So you should look at redshift of, let us say, 20. We right now do not have any data which looks up at redshift of 20, but in this analysis of stochastic gravity, from here you can compute more and more terms, more and more correlators which will show you of the non-classical nature. So stochasticity will maintain a stochastic correlator structure later on. So more and more higher point correlators which will be available in, let us say, next set of CMB observations, where right now we do not have enough precise data to look for minute correlations. So non-Gaussianity, for example, will suggest that something different from the initial start story is there. Once that signature is there, my claim is that it will affect your analysis of energy budget of the CMB, energy budget of the universe in the late time, and that will affect the evolution of the CMB redshift 30 onwards.
So only non-Gaussianity.
Non-Gaussianity is a marker of things which are going to become interesting. You have to recalibrate your thing looking at that and find out what is the new analysis which is suggesting how much of CMB anisotropy you should see after 32 right now. Right now we are taking the data what we see today is a direct mask to what happened at LSS. I'm saying this story has a junction in between. You have to go through that junction slightly carefully. You cannot extrapolate the data as of now just to the last casting surface. So observation wise, we have one observation. Interpretation will change, that it is not just the map of CMB, but CMB plus something interesting happening at late times.
Okay, let us thank Professor Lochan.
Recording in progress.
It was quite complicated. If you use the Fourier space approach, you will find that there's no signal. I've seen papers to that effect in the cross.
Well, if you
Hello?
can share with me, I will be happy to
Yeah.
read it.
Hello, Professor Martin. Hello.
Hi.
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 Okay. Okay. So we can hear you. Uh, so
Sorry.
okay. So let us start the talk of Professor Martin. We will be talking on the probing the primordial universe with cosmological surveys. Okay, Professor Martin, please start.
Thank you very much, and thank you to the organizers for inviting me. And I'm sorry that I couldn't be there in India. Can you see my screen? Hello?
Yes, we can see.
All right. So I want to talk to you today about probing the primordial universe with cosmological surveys. This is this amazing possibility that we can use galaxy surveys in the late universe to try to dig out primordial signals from inflation, from the birth of the universe, more or less, simply by looking at patterns or smoking gun signals in the distribution of galaxies. So to do this, we need next generation galaxy surveys. So let me just quickly introduce you to some of them and some of the ones that I will talk about. First of all, there's DESI, the Dark Energy Spectroscopic Instrument, which has already started observing some amazing papers already coming out from the early data releases of DESI, but it's still a next generation survey. It'll be continuing for the next few years. Then there's Euclid, which has both spectroscopic and photometric surveys, and that has started observing. It was put into orbit quite a while ago. That's another next generation pair of surveys, photometric and spectroscopic. I'll mention both of them. And then there's the Legacy Survey of Space and Time on the Rubin telescope in Chile. That is due to start observations next year, I believe. Very exciting. So these are all optical infrared instruments counting numbers of galaxies. And then, sorry, next one. And then, of course, we have the 21 centimeter surveys. And you've just heard the talk before the previous one. You heard a very nice survey of 21 centimeter intensity mapping by Alessandro Marins. And I will be using that concept in my talk. But the SKA, the Square Kilometer Array Observatory, plans two types of instruments. On the left, the dish instruments, which can perform galaxy surveys in the post-reionization universe, and on the right, the low-frequency antennae, which look at the epoch of reionization, which I won't discuss. I will point out that the precursor of the SKA mid telescope, which has 64 dishes, has been taking observations since 2019, and it includes a proposed cosmological survey, which hopefully will be up and running in the next year, but the SKA itself is due to begin observations in 2028. That'll be roughly double the size of Meerkat and growing some more if funding permits. So what is the special thing about 21 centimeter? This is the 21 centimeter emission line of neutral hydrogen, and in the post-reionization period of the universe that I'm thinking of, nearly all the neutral hydrogen in the universe is trapped inside galaxies. And this emission line, because it's an emission line, it's a sharp emission line, it gives you an extremely accurate redshift. As soon as you image a galaxy in the H1, in the radio band, you immediately have its redshift to extremely high accuracy, more accurate than any of the optical spectroscopic surveys. And this 21 centimeter arises from the spin-flip transition. I won't say much about it because Alessandro has already given you an introduction. The problem with it is that it's a very weak transition and the signal is very weak. So what I show here is a simulation of H1 emission from galaxies out to redshift 5, but the signal is very weak. So what this means is that when trying to detect individual galaxies by their H1 emission, the initial version of the SKA is likely to only be able to cover 5,000 degrees of the sky out to a redshift of about 0.5, simply because it takes so much effort and so much collecting area to detect this weak signal and identify individual galaxies positively. So that galaxy survey is not going to be competitive with optical infrared galaxy surveys, which therefore seems that there's not going to be any transformational cosmology with the SKA. But of course, as you now know from the talk by Alessandro, it is not essential to resolve individual galaxies in order to do precision cosmology. And if we are content to add up the signal from H1 emission in galaxies in each pixel, we don't detect the individual galaxies, but we still see the fluctuations in principle from cosmological perturbations and large-scale structure. So the integrated emission, the brightness temperature in each pixel is what's measured in 21 centimeter. In principle, it gives us an extremely rapid survey mechanism to cover huge volumes of the sky. For example, SKA intensity mapping goes out to redshift 3 with a proposed sky area of 20,000 square degrees, operating in single dish mode like bingo. Of course, the problem is the foregrounds, which I won't go into because Alessandro gave a very thorough and interesting description of the problem of foregrounds. That obviously is an issue. So this is a little bit like doing the CMB at any chosen redshift that your telescope is tuned to. So at each particular frequency, i.e. each redshift in the range, say 0 to 3, you have a map of the sky, which is a bit like the CMB. It's a similar idea, and just like the CMB, it faces foreground contamination. But because it's lower frequencies than the CMB, the foregrounds are worse, they are bigger. Nevertheless, a lot of progress is being made to deal with these foregrounds. And I'm not going to go into that because I'm focusing on the primordial cosmology to do with non-Gaussianity. So I have mentioned Meerkat, the precursor to the SKA mid array. It is going to be a pathfinder for 21 centimeter intensity mapping through MeerClass, the Meerkat Large Array Synoptic Survey proposed by Mario Santos and his team here in Cape Town. Yeah, this cartoon just shows the history of the universe from the Big Bang, the unknown Big Bang, through inflation, through the last scattering surface, which gives us the CMB map of the sky, through the dark ages when neutral hydrogen dominates the baryon budget, and then the cosmic dawn when the first stars are formed to light up the universe, the reionization period which follows that, and then the period of the growth of structure after reionization, when the neutral hydrogen is more or less all trapped now in galaxies as the universe has reionized. So again, you can see on the right the galaxy map at a particular redshift, say Z equals 1, and then the intensity map of the galaxies inside it. Right, so back to the primordial universe, the question of how can we probe the primordial universe? Well, the link is clear if you think about the generation of fluctuations during inflation, and you realize that those fluctuations are the origin for the CMB temperature anisotropies as well as for the large-scale structure. So it's therefore not too surprising that the properties imprinted during inflation would in principle be carried into the CMB and even later in time into the galaxy distribution. So that's the basic idea. And if we look at the simplest models of inflation, particularly the single field slow roll inflation models, they are essentially Gaussian. But as soon as we start introducing complications, and in particular introducing additional fields during inflation, additional light fields, we come up with models which generate can generate significant primordial non-Gaussianity in the fluctuations. These quantum fluctuations, therefore, can be born through the quantum process with a significant or an insignificant amount of non-Gaussianity, depending on the model of inflation. And those same quantum fluctuations get stretched by superfast acceleration during inflation to become super Hubble, and then therefore to become classical. And these are the perturbations which generate temperature anisotropies and density perturbations that lead to the large-scale structure. So if the imprint of any primordial non-Gaussianity exists in the later fluctuations, which it does, but the question is, does any of it survive? If that survives in some form, then we would have a method to probe models of inflation, potentially to rule out large bodies or large families of models if we detect, for example, significant non-Gaussianity in large-scale structure or in the CMB. We could rule out the simplest models of inflation. So that's the basic idea. Just to summarize on this slide, I've put these bullet points that non-Gaussian primordial perturbations are actually more common in terms of the number of models that generate them than the simplest models, which are essentially Gaussian. And although different forms of non-Gaussianity are important, I'm going to focus, because I'm looking at galaxy surveys and their power spectrum, I'm going to focus on the local form of primordial non-Gaussianity, which is characterized by a parameter FNL. And if FNL is found to be definitely non-zero, then that would rule out the simplest models. If it's found to be not only non-zero, but less than or of the order of 1, then many multi-field models would be ruled out. So in a sense, the closer we can get the error on FNL to 1 and below 1, the more power we would have to discriminate between inflationary models. So in a sense, the target is something like sigma FNL, the error in FNL, to be 1 or less, if we really want to be ambitious. Now, what happens to these primordial fluctuations? I'm not going to talk about the CMB because I'm focusing on galaxy surveys. So let's look at perturbations in the matter. If you look at nonlinear scales, it's clear that nonlinear perturbations are, by their nature, non-Gaussian. And strong nonlinear clustering leads to high levels of non-Gaussianity. It doesn't take long to check and to confirm that primordial non-Gaussianity is wiped out on small scales. The primordial signal is lost because it's overwhelmed by the process of gravitational instability. However, if we think about the large scales, then the picture is different. So on very large scales, where structure formation is essentially not causing visible clustering, the perturbations remain linear effectively. Nonlinearity doesn't really arise on these ultra-large scales. And so any primordial signal of non-Gaussianity would be frozen in to these ultra-large scales and in principle be a smoking gun signal. This, in fact, affects both the CMB and the large-scale structure. This cartoon gives us the general idea. The FNL is imprinted during inflation by the particular kind of inflation model that is most likely to have initiated structure formation in the universe. That same constant value of FNL affects the temperature anisotropies in the CMB, which Planck and other experiments are measuring. And the same FNL survives through density perturbations into the galaxy distribution post-reionization. In between, of course, that's also the same FNL, but I'm talking about post-reionization in this talk. Well, the state-of-the-art precision on FNL comes unsurprisingly from Planck. Planck has given us this remarkable precision of an error of 5 with a best fit value of minus 0.9. But since the error is much larger than that, we still don't know whether FNL is positive or negative. But nevertheless, we have a precision of 5 as established by Planck. By the way, I should just mention that the CMB power spectrum, being a Gaussian two-point function, a Gaussian correlation function, does not carry any signal of non-Gaussianity. So the lowest order spectrum that does have a signal is the bispectrum, and this result is based on the CMB bispectrum. It turns out that Planck is quite close to the cosmic variance limit. Future surveys will improve this somewhat, but not significantly. And therefore, we need to invoke the three-dimensional matter surveys via galaxy surveys of 21 centimeter intensity mapping, which have a lot more modes than the two-dimensional CMB. Of course, the price that we pay for that is that they're much more subject to nonlinearity and astrophysical systematics than the CMB is. So as I've mentioned, the power spectrum is not affected by local primordial non-Gaussianity. That's true for the CMB, and it's also true for dark matter. But because galaxies are traces of the dark matter, bias traces, they are sensitive to the bias. The non-Gaussianity affects the bias of galaxies, so that we go from on very large scales, we go from a scale-independent bias, which depends only on redshift in the Gaussian case, to a scale-dependent correction coming from primordial non-Gaussianity. So this particular effect, which is essentially due to the matter bispectrum, in some quite subtle way, shows that the power spectrum of galaxies and other traces of the dark matter acquires a scale-dependent bias in the presence of local primordial non-Gaussianity. And this scale dependence goes like 1 over k squared, or more specifically like h squared over k squared, where h is the conformal Hubble parameter. And so it's only on the very largest scales, certainly scales less than the equality scale, that the signal becomes non-trivial. So this signal is imprinted on the very largest scales in galaxy surveys in principle. When I talk about ultra-large scales, if we look at the matter power spectrum here, K equality is the scale of the turnover. To the right is the smaller scales, BAO scales, and then nonlinear scales, and to the left are the ultra-large scales, including eventually the Hubble horizon scale. But it's in this region here, you need surveys that are going to probe around and beyond the equality scale in order to pick up this signal, which is going to be suppressed by this factor h squared over k squared. So as a consequence, we need surveys with ultra-large volume, high redshift, big sky area, preferably both. Now, the catch now is that the larger the scales that you probe, the less number of pairs of galaxies or pairs of fluctuations that you have on those scales. And so the higher the cosmic variance. And this cosmic variance grows very strongly on large and ultra-large scales. And it turns out that this is a fundamental limitation. Although the next generation surveys which I've talked about can more or less match the CMB in the best cases, sometimes a little bit better, they can't really get to 1 and below. That's the future target that we would benefit most from. And so it seems that the task is more futuristic than we'd expected. But in fact, there is a way around this problem, and that is the so-called multi-tracer method. So the multi-tracer method is just very naively and briefly summarized in this cartoon here. If we have an underlying realization of the dark matter field of our universe, and we have two traces which on mapping this underlying distribution, tracer 1, say galaxies, tracer 2, say 21 centimeter intensity, then you can think of taking the fluctuation fields delta 1 and delta 2 and dividing them and ignoring redshift-based distortions and lensing and other effects. You can see that the ratio of the two stochastic deltas is a non-stochastic function, the ratio of the biases. So in the simple-minded case, you can identify the ratio of the biases without cosmic variance. That's the basic idea. Of course, it's a bit more complicated than that, and we have to bring the noise in and the redshift-based distortions. But essentially, this gives you an idea as to why having two different traces with different biases allows you to get around the problem of cosmic variance. And it's obvious that for best results, you want the biggest difference between the biases. If the biases are exactly the same, then you get nothing. So the more different they are, the better. And you also want, preferably, surveys whose systematics are as different as possible, because on very large scales, the systematics are a huge problem. And if the systematics don't correlate, then we gain a further advantage from the multi-tracer. So in this talk, I'll mainly just give you the example that was worked upon of using 4 spectroscopic surveys. The 2 bands of the SKA 21 centimeter intensity mapping surveys, the band 2, which is the low redshift one, and band 1, the high redshift one. In each case, multi-traced with a galaxy sample. So we take the low redshift bright galaxy sample of DESI, or the H-alpha spectroscopic survey of Euclid. So we get these 2 multi-tracer pairs, and then we combine all 4 of them together in a 4-tracer, multi-tracer combination. So what do we get from this? So, well, first of all, the advantages that we have from taking these 2 pairs is that we have huge volumes. The sky area, I'm assuming, is about 10,000 square degrees overlap between these surveys. The sky area is big, and the redshift, of course, in the low case is not so high, but in the high redshift case, we have a very deep redshift, common redshift range, which is beneficial for a signal such as PNG. Now, in order to stay as close to the actual observations as possible, we use the angular power spectrum. There's another reason for using the angular power spectra, and that is the following, that if we use Fourier power spectra, we almost always assume a plane parallel approximation, a flat sky approximation. And we almost always neglect lensing. But wide angles and lensing effects are crucial to include if we want to go after an ultra-large scale signal. And the angular power spectrum naturally incorporates all wide angle correlations, all lensing effects, and in fact, all observational effects, theoretical observational effects, are naturally incorporated in the angular power spectrum. And furthermore, no Alcock-Baksunski correction is required because the angular power spectra correspond directly to the data. There is no need to choose a fiducial model in analyzing the data using angular power spectra. So the angular power spectra includes the FNL signal inside the bias here. Then there's redshift space distortions plus lensing plus other effects which come in as well and which need to be incorporated for theoretical accuracy. So we use a Fisher matrix formalism. In the angular power spectrum case, you take the trace of the parameter derivatives of the CLs with the covariance matrix in this form of a 4-matrix product. And the covariance matrix includes the noise. In the case of 21 centimeter mapping, just as an aside comment, the noise is primarily thermal noise. The shock noise on linear scales and large scales is much smaller than the thermal noise, and so we can neglect it. I'm not sure exactly what time I have, but I think I should be coming to a close soon, so I'm nearly there.
You
These
have
are the
time,
results.
10 minutes you have still.
10 minutes still.
Yeah.
Oh, okay. Thank you. So this table summarizes the results that we found in this paper 2021. For the low redshift combination here of BGS from DESI and IM2 intensity mapping band 2 from SKA, you can see that individually, say you've got 15,000 square degrees of DESI, we only get an error of 26, 27 on FNL, because the redshift is just too low here. 20,000 square degrees for SKA allows us to get only 35.7. Yeah, that's basically because of foregrounds as well. We had to cut out some of the ultra large scale signal to get that. But look, if we assume that the overlap sky area is 10,000, you can see the redshift overlap is almost complete, almost perfect. The multi-tracer gives us a huge improvement. We get down to 2.1. It's quite remarkable. Now, if we look at the H alpha Euclid spectroscopic survey, 15,000 square degrees, that gets you about 9. Quite disappointing, but that's what it is. The band 1 SKA over 20,000 degrees with a higher redshift gets us much better, 4.7. And when we combine them, we get down to 3. And then when we do the 4-dimensional multi-tracer, all combined together, we get down to 1.5. So the figures are not so important. They just give you an idea of the level of improvement that you can get. And let me also point out that this figure 1.55 here, just like the other two boxed figures, that is simply from the smaller part of the pair of surveys that you can combine. Then what you can do is you can go back to the rest of, say, example here, there's another 10,000 square degrees of SKA that I can use, and another 5,000 square degrees of BGS. I can add that Fisher information and get it below this figure. Similarly, I can get actually down to more or less 1 or even a little bit below if I add the non-overlap information, which I haven't bothered to show here. So one of the lessons we learn from this is that we could actually do better with photometric surveys. It turns out that redshift accuracy is not the most important thing for going after local primordial non-Gaussianity. What is more important is a high number density. Now, 21 centimeter intensity mapping has a high effective number density, and there isn't a photometric version of it. That's what it is. But instead of using spectroscopic galaxy surveys, we could look at the photometric surveys. And the principal next generation photometric surveys are LSST and Euclid. So if we replace the Euclid spectroscopy that we were using by LSST photometry, we find that just from that pair, SKA band 1, the high redshift with LSST, we can get to 1 and even below 1 if we ignore systematics. I must say that all of these Fisher forecasts are optimistic because they don't incorporate systematics. So they're just, the most important thing is to see the level of advantage you get over the single tracer rather than to think that the final Fisher forecast is accurate. It ignores systematics, so we shouldn't rely on it too much, but it does give us an idea of whether or not it's worthwhile using this method in upcoming surveys, to which the answer is clearly yes. Now, we could improve on this further by adding LSST and another survey, if we like, adding extra surveys, adding Euclid photometry, adding other surveys. I haven't gone into that. There's some work in progress doing that. More importantly, we could add CMB information. See, the CMB lensing map allows us to break some of the degeneracies that exist even in the multi-tracer between galaxy surveys of different types. So my last slide is just to show you some older work in which CMB lensing was added to a multi-tracer of 2 surveys. So in this case, the Euclid is the photometric Euclid and there's LSST, but the specs are a little bit out of date. This is a 2019 paper. The dashed curves show the improvement in precision that you can get if you include CMB lensing in the multi-tracer. So you have two surveys, intensity mapping, galaxy survey, and CMB lensing. It's a 3-tracer CMB multi-tracer. And you can see this earlier quote was showing that SKA and LSST could just about get to 1. SKA and Euclid photometry, same. It's not, you can't really distinguish much between these forecasts here. And then with, SKA and Euclid was this green one here. Yeah, this one seems to have done the best. So I think I should end there and allow for some questions.
Okay. So, any question?
Can I make a question?
Please go ahead, Alessandro.
Yes. Can you go back, I believe it's 3 slides when you show that table with
Yes.
results for sigma FNL? Yes. For instance, what do you think is the most challenging information that can provide these high values, even if you combine different multi-tracers? For instance, is it because of the H1 noise, or because of the noise provided from the galaxies? Because, for instance, we know that system temperature from H1 provide a high influence on the final results. I'm not sure if it is a point that can be improved, that type of values, if it is from, for instance, noise itself or not.
Well, let me just comment that we assume that the background temperature is known. And of course, that's a big assumption. But what I could say before I try to go further on the details, these results are similar if you combine 2 galaxy surveys. So they're not special to intensity mapping.
Okay.
Intensity mapping has the problem of foregrounds. The noise is not an issue with intensity mapping. It's just that it's not Poissonian. It's thermal noise. But I think we can deal with the noise. It's not that. It's not as if it is quite large in the case of SKA, but it's not itself a major problem. The foregrounds would be, in practice, the biggest problem. So the foregrounds lead to a loss of some of the very large scale modes.
I see. Thanks.
Okay. If there are no more questions.
Hi, Roy. Sami here.
Hi, Sonny. How are you?
So, yeah, so let us suppose in galaxy surveys you find large value of FNL tomorrow, okay? So, what implication it would have for the primordial cosmology, say, for primordial black holes and related issues? Would it have some implications for, say primordial black holes?
That's a good question. I don't actually know the answer, but I'm guessing that the primordial black holes arise from tails in the distribution, non-Gaussian tails on very small scales. And galaxy surveys, by contrast, are probing non-Gaussianity on very large scales. So it may be that looking at the galaxy bispectrum and the 21 centimeter intensity bispectrum, which combine large and small scales, and especially in the squeezed limit, which is appropriate for local primordial non-Gaussianity, it may be that the bispectrum of these surveys could somehow be sensitive to spectra that produce primordial black holes? I'm not aware that anyone's looked at that, so it's an interesting question, and I'm not sure what the answer is, but I'm guessing that the answer will involve the bispectrum.
Okay, so let us thank Professor Martin.
Thank you.
So we have almost reached the end of the conference, and I would like to ask Professor Shushkov and Professor Toporonsky to say a few words as a closing remarks. Yeah. Oh, okay. So I think, yeah. So Roy, I think, can you hear me?
Yes.
Yeah. So yeah, please say a few words as we are starting this closing remarks now.
Sorry, you want me to say something?
Yeah, so we are about to close this ceremony. So if you could say a few words.
Well, I hadn't prepared anything, but let me just repeat that it's been an honor to be invited to this 4th symposium of the BRICS Association for Gravity, Astrophysics and Cosmology. And it's wonderful to see that BRICS AGAC, under the leadership of my colleagues, some of whom will speak after me, has managed to grow and to flourish so that we actually have our 4th symposium. And I hope that in the future, we will continue from strength to strength. I think there's a lot of science cooperation and a lot of synergy between the astronomers working in these the different BRICS countries. BRICS itself is actually getting bigger, so that synergy will grow. So thanks to the organizers for the efforts to put together this 4th symposium. Again, I apologize for not being able to be present, but it seems to me that it's been successful, and I congratulate you on that.
Okay, thank you, Roy. Professor Toporonsky, please say a few words.
I also haven't prepared, so there are not many words. I just remember I participated in the third BRICS symposium in Kazan 5 years ago. So that's why, what I can say, after a big break, BRICS association shows that it is still alive. It's very good. Because to be alive, not to be alive, it's the only thing which cannot be corrected. We are alive.
Professor Shushkov, please.
Well, nobody is prepared to say a final speech. But anyway, first of all, I am happy that the conference happened. Now we should say that the conference happened, and the conference was quite successful. And actually, it's very good that our association is alive and working. I hope that next conference will be in Brazil. And Roy, we discuss it. Also, I would like to say that this conference was very useful and interesting personally for me. And actually, I have some contacts in my email list. I show my phone and also my heart. Probably, yeah. I think that this conference will be useful not only for me but for all of us. And my congratulations to all of us. And once more, let me say the words of gratitude, very, very big gratitude to organizers of this conference, because local committee
was working just brilliant, and my special words to Sami, who made very, very much efforts to organize this conference. Thank you so much.
So again, thank you everyone for coming and making this conference a huge success. And goodbye, and I wish you a Merry Christmas and Happy New Year to all of you. Thank you.